Hello everybody, Mr. Chan here, starting another lesson for Algebra 2, Lesson 3-3, Polynomial Identities. Grab your note taker, Student Companion, and turn to page 69, and let's get started. All right, so when it comes to polynomials, there are some properties involved that are kind of unique and fascinating. We are going to start with something called Pascal's triangle. Right there on page 69, you see kind of a triangle with a bunch of ones down the left side and a bunch of ones on the right side. To get through the number like this right here, 2, the pattern is to add the previous two numbers above it. So it's the sum of the two numbers above. This pattern is named after Pascal. And famously, this is called Pascal's triangle. Now follow along here. We're going to continue with this pattern for a few more rows, because right now we have technically 6 rows, but we don't call them 6 rows. We call the first one row 0, and we're going to pick an integer n equals 0 for that first row to indicate that. That's row 0, and then it moves up. Row 1 is below row 0, and so on and so forth. Jot this down. So the index number for these values are linked to these polynomials, and I'll show you how they're all connected together in a minute. But right now we're going to pick n, the integer, to represent each of those row numbers. We're going to continue on with this pattern. So writing the n equals 6 row, I have 1. Then above it, I have 1 and 5 go give me 6. And then I add 5 plus 10, give me 15, and so on. There definitely is symmetry here, but there are a lot of unique properties to Pascal's triangle that show up with polynomials and, surprisingly, probability you'll learn in your other classes in the future. Let's do one more and see what happens here. So that gets me to n equals 6, 7, and 8. Okay? We'll come back to this in a moment and talk about how this is linked to this section. And that linkage is called binomial expansion. Binomial meaning taking a 2-term polynomial like x plus 5 or whatever. We'll just generically represent it with a binomial here, a plus b, and bring it to any power, and this is the connection here, n. See that n right there? N is linked to the row number as well. So if I bring it to n equals 0 or n to a plus b to the first, second, third, the row values that you see in Pascal's triangle are linked to this expansion. All right, before we go further, when we do an expansion, what we're referring to is we're simplifying or multiplying the power, okay? That's what we're doing. So when we do that, we need to bring up some things that we learned in Algebra 1 and Algebra 2 so far when it comes to polynomials. Here are some identities that we need to write for review. Some polynomial identities that you've learned so far. They include the most famous difference of squares. That's coming up. Let's write that down. So back in Algebra 1, you saw something like a squared minus b squared in many types of forms. And generically, when you factored a squared minus b squared, because there's a binomial there, there's a minus sign, and those two terms are square rootable, it factors to be a minus b times a plus b. This is something you learn in Algebra 1. And that particular answer you got was called a product of a sum and difference. So let's recap here. Going from a squared minus b squared to a minus b times a plus b was something called factoring. Factoring means to break it down into its parts, dividing it into pieces. So some of the properties I'm going to throw here are factoring properties, going from left to right. Going in reverse, opposite of division is multiplication. When you do a product of a sum and difference, you do end up with a difference of squares. That would be called simplifying or multiplying, going from right to left. Here are some other properties that are important. So here's one property, difference of squares. The second one that you learned already, difference of cubes, is brand new. And I need to bring up difference of cubes. And we have something called sum of cubes as well. This is brand new now for a lot of you, so watch this. Just when you thought there was only one particular factoring pattern called difference of squares, we have a difference of cubes that works out too. A cubed minus b cubed can be factored. Isn't that weird? It comes out to be this: a minus b times a squared plus ab plus b squared. That is horrendous, doesn't it? Looks ugly. We also have something called a sum of cubes, interestingly enough. We don't have a sum of squares, but we do have a sum of cubes. Here's what a cubed plus b cubed factors to. A plus b times a squared minus ab plus b squared. Now, if you do a quick comparison between difference of cubes and sum of cubes, they look very, very pretty much the same in terms of the letters and the powers, but the signage is a little different, okay? So that's kind of interesting there. All right. One other thing that I want to bring up that we'll be using soon, it's called the square of a sum. If we take a binomial and square it, we'll get a squared plus 2ab plus b squared. This is a perfect square trinomial. Now don't freak out. I'm just reminding you of things that you've seen before. A plus b squared was literally a plus b times itself, right? And I'm trying to make a connection with this Pascal's triangle. When you foiled a plus b times a plus b, you got this particular perfect square trinomial. Interestingly enough, the numbers in front of the perfect square trinomial is linked to Pascal's triangle. Look at it. We have a 1 here in front of a squared, a 2, and a 1. 1, 2, 1. Where do you see that? There it is. It's in Pascal's triangle where n equals 2. And the 2 is referring to this n right there. Bam. Isn't that weird? The leading coefficients of the simplified polynomial is linked to Pascal's triangle. Let that sink in for a little bit. Let's move on to the next page. There we go. All right. Oh, we didn't answer C, did we? Write a formula for the sum of the rows in the nth row of the, oh, that's interesting. Another pattern that pops up is if you were to add the numbers up for the rows of Pascal's triangle, we won't necessarily come up with a fancy formula. Well, we can, I guess we can. But if we take a look at Pascal's triangle and add up the rows here, let's do that. See what happens. All right, row 0, you add up that, I'll get 1. Next one, you get 1 plus 1 is 2. Next row is 1 plus 2 plus 1 is 4. Next row is 1 plus 3 plus 3 plus 1 is 8. Interesting. You guys see an interesting pattern. The next one will give you 16. The next row will give you 32. Look at that. Looks like it's doubling. In fact, if it's doubling, it is a power of 2. Isn't that interesting? 1, 2, 4, 8, 16, 32 is the pattern. Another coinky-dink in Pascal's triangle. In fact, in algebra, you can represent this pattern 1, 2, 4, 8, 16, 32 as a power of 2. 2 to the 0 power is 1, 2 to the first is 2, 2 to the second, and so on and so forth. That is the formula. Isn't that cool? Next page. Here we go. Okay. I'm going to prove the difference of cubes identity. Now let's remind ourselves, because we are on a new page here, let's write them out for a little bit. Those formulas from the previous page. Difference of cubes states a cubed minus b cubed can be factored to a minus b times a squared plus ab plus b squared. That's crazy, right? We're going to take that and we're just going to go ahead and FOIL that right here. And when we superfoil it, we'll see what happens, okay? Here we go. I'm just going to rewrite it and FOIL it. We have a binomial times a trinomial. When we do that, we're going to end up with 6 products. Here we go. A times a squared, a times ab, a times b squared. That takes care of the first half of the product. Let's do the second half here. Negative b times a squared is minus a squared b. Notice I already kind of see a pattern and a connection here. Notice how I kind of lined those like terms up a little bit. Here's another one. Negative b times ab is negative a b squared. And then we have negative b times b squared is negative b cubed. Did I make a mistake here? A cubed, a squared b, a b squared. Yeah, I did. I left out an a. Wow. That term right there should have been a b squared. Good thing I caught myself. That would have been embarrassing. I was wondering why it looked kind of weird. So with the 6 products here, 4 of them cancel. They zero out right there and right there, right? What are you left with? Isn't that crazy? You're left with a cubed minus b cubed. Whew, good thing I caught that. There's your proof right there. Okay, all right. So my point is this. The same goes for the sum of cubes. And I'm going to write down here just for reference and to see it for practice here. The proof itself comes out the same as well. I remember my algebra teacher making us memorize these formulas, and I was like, oh, but it really doesn't take too much time to kind of memorize it. Any questions by example 1? We will skip the habits of mind right there and move on to example 2. So far, we learned how to factor. We've proven the factoring pattern. We're looking for cool patterns in Pascal's triangle as well in a moment. But let's think about these polynomials that are given to us. For the rest of the lesson, think about what we're doing. Look at example 2. It says multiply polynomials. Think about that for a second. What happens if you multiply polynomials? Then they switch gears and move to example 3, and hey, let's go backwards on multiplication. Let's do dividing or factoring polynomials. So I hope you understand that we're just multiplying some problems sometimes, and sometimes we just go backwards on multiplication or divide or break it back down into its parts. So right now with example 2, we're just multiplying and looking for patterns. What they want you to see in example 2a is, hey, it's not just another problem, but think of 3x squared plus 5y cubed times its conjugate, 3x squared minus 5y cubed, as following a pattern. Think of it as a plus b times a minus b. Whoops. And we know doing a product of a sum and difference will yield you a squared minus b squared. That's the pattern. Identifying a as 3x squared and b as 5y cubed will help you with this pattern and save you some time. A squared minus b squared. Now, it's not going to save you time all the time, but here we go. All we have to do is basically put it into the spots. I mean, if you didn't know this particular pattern, nothing stops you from actually foiling 3x squared plus 5y cubed with its conjugates. But knowing the pattern, we're just going to literally throw those in. 3x squared right there, and 5y cubed right there, and just simplify this part, and we're done. That's the key to these patterns. It's not the end of the world if you don't do that. 3x squared squared is literally 3 squared is 9, x squared squared is x to the 4th. Minus 5 squared is 25, y cubed squared is y to the 6th using power rule. And that is the answer. Could you have gotten that just by foiling it? The answer is yes. All right. So that's what we did. We substituted 3x squared with a, recognizing that pattern. So this is a product of a sum and difference, yielding difference of squares. Pattern. All right. Number 2b, we have 12 plus 15. Okay. We'll see this as a product of a sum. The sum being 12 plus 15. 12 is A, 15 is B. We know the pattern is A plus B, now we didn't expand it yet, but A plus B times itself is equal to A squared plus 2AB plus B squared is the pattern, okay? So A squared plus 2AB plus b squared. Now just keep in mind, it's not the end of the world if you don't know these patterns. You just go ahead and FOIL it. All right, a is 12. Put that in those spots right there and right there. B is 15. Put it right here and right there. And simplify it. That's it. 12 squared is 144. 2 times 12 times 15 is 360. Trust me. And 15 squared is 225. Add that all up, you get 729. And that's your answer. Yay. Could you have gotten that by doing 12 plus 15 for sure? Of course. Of course, no big deal. The point is to practice those patterns, right? 12 plus 15 is 27. 27 squared is literally 729 that we got from earlier, okay? All right. So we just did a couple of problems involving multiplication of polynomial patterns, okay? The point is to look for those patterns. Now, switching gears. We're going to go backwards. So of multiplication, we're going to go dividing. Now we call that factoring in algebra. Gets a little hairier. All right. You may not see it on my video here, but let me write those 3 particular identities. So I will use them in the next 3 examples here. So please be patient with me. This is a little redundant for some of you, but being that the identities are off screen, I'm going to write them down here. And we're going to utilize them. This example involves factoring, so I'm writing the patterns for factoring. Okay, these are factoring ones, going this way. Going in the other direction is just multiplication or simplifying. Just to show you, okay? All right, number 3A is a very challenging problem. Identifying these gives you an advantage because you know the formulas. M to the 8th minus 9n to the 10th we know as a binomial. Looking at my list here, on the left here, we have a squared minus b squared and a cubed minus b cubed. It's one of those 2 maybe. If we check to see if m to the 8th or 9n to the 10th are perfect squares or perfect cubes. Now, m to the 8th is hard to tell because the m to the 8th is bothering you, right? 8 is not the number you look at when it comes to powers. You look at the number 1 in front of that. 1 is a perfect square and is also a perfect cube, so that doesn't help us. Looking at number 9, the value 9, 9 is not a perfect cube, but it is a perfect square. So let's think about this for a second. M to the 8th is square rootable. When it comes to powers, the square root of m to the 8th is not square root the number 8. You take half of that. Half of m to the 8th is m to the 4th. This is a perfect square. It works. 9n to the 10th, you can take the square root of it because half of 10 is 5. Those are perfect squares right there. Let me show you in a second, okay? So think of m to the 8th as, let's rewrite that a little bit. M to the 4th squared. You see the power there? 4 times 2 is 8. That's why 8 is a perfect square power, okay? And then over here, minus the square root of 9 is 3. The square root of n to the 10th is n to the 5th because you take half of that squared. That's crazy, isn't it? M to the 4th is your a value. 3m to the 5th is your b value. We have a difference of squares here, ladies and germs. The first formula, very difficult to spot, not easy to teach whatsoever. Pause the video for a little bit. Think about that formula. I broke down the m to the 8th and I broke down 9n to the 10th. Okay? Using the rest of the formula, this is equal to A minus B times A plus B. I'm literally going to take the square roots of those original terms from the beginning. A minus B times A plus B. And we just factored something that was very difficult because it was hidden. That is your answer right there. Isn't that crazy? That is a product of a sum and difference. Well, the way I wrote it's a difference in sum, but the way we call it is a sum and difference. No big deal. All right. Woo. So pause here if you have to and take a look at what just happened. I took this formula and applied the A and the B and got an answer. Okay. All right. Next one. 27x to the 9th minus 343y to the 6th. Holy cow. We know it's going to be one of these right here. We don't know which one. So we need to check to see if the terms are square rootable or cube rootable. 27 and 343, no, you can't do anything with either of them in terms of factoring out a monomial GCF. However, 27 is actually a perfect cube. This might be a great time to start thinking about perfect cube numbers. Making a list off to the side or something. Let's do that right now, just for the heck of it. Why not? And we already know about the perfect square numbers, right? 1, right? 4, 9, 16, 25, 36, 49, 64, and so on. Some of you might make that list here for perfect squares and seeing that pattern in the future. Perfect cubes are a little tougher. Let's try them. 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed is where I start losing my mind here. But make a list. Yeah, look for those numbers. 27 is in my list right there. Okay. But guess what? 27 x to the 9th is cube rootable. Minus 343y to the 6th is also cube rootable. Let's do that. Isn't that crazy? That's cube rootable, and that's cube rootable. It is a difference of cubes. That is a difference of cubes. We're looking for patterns. The cube root of 27 is 3. The cube root of x to the 9th, to deal with powers, what you do is you take the power and divide by the index 3 in this case. 9 is divisible by 3. 9 divided by 3 is 3. 3x to the 3rd is the cube root of 27x to the 9th. So that's 3x to the 3rd power, okay? Power right there. Minus 343. 343, you're going to learn sooner or later, is also a perfect cube number. That is the cube of 7. Y to the 6 cube rooted is 6 divided by 3 is squared. Isn't that crazy? Bam. So there it is. There's your A value. And here's your B value. We're going to put that into this formula. I know, you're not going to like the answer. The answer looks messier than the original problem. But to factor in this difference of cubes, it will look like this. A minus B times A squared plus AB plus B squared. Crazy, isn't it? Let's put those numbers in. and simplify it. I like to do this first. A, and then I'm going to put in the B's. B, B, B. Now think about this. Because of these patterns, we can factor very ugly binomials and very ugly trinomials, right? All right. We do need to simplify parts of this right there and right there and right there and get a final answer. Here we go. So this is 3x cubed minus 7y squared times 3x cubed squared is 9x to the 6 plus 3 times 7 right there is 21x cubed y squared plus 49y to the 4th. That's your answer. Now, I could theoretically ask you guys to prove this by superfoiling that. If you superfoil that product of a binomial and a trinomial, you'll end up with this answer right there. Trust me, okay? Okay, woo. Last one. On example 3, we have a, well, this is kind of strange. We have 12 cubed plus 2 cubed. That looks like a sum of cubes, doesn't it? Literally a sum of cubes. That's what we have, and we're literally going to grab that formula, okay? I think the point of doing this is to show you how things are buried. A is 12. As you can see right there, that's your A value. And B is 2. Okay? So this literally is equal to A plus B times A squared minus B, AB, and plus B squared. So let's put those numbers in. A is 12. And B is 2. I'm just using that formula, the third formula off to the left, and clean this up. Wow. This is like a roundabout way of solving problems. And you just go and simplify that, right? 12 plus 2 is 14. I know this is crazy. 12 squared is 144 minus 24 plus 4. This equals to 14 times 144 minus 24 is 120. 120 plus 4 is 124. I know, this is pretty crazy. And that will give you 1736 when you multiply those, okay? I know, you could have done 12 cubed plus 2 cubed, and you'll get the same answer. All right. Woo. Taking a look at the habits of mind, what binomial has factors a minus 3b and a squared plus 3ab plus 9b squared? But basically, they're asking me, what would happen if you multiply this binomial with this trinomial, okay? When we do that, well, we can manually do this, but what's staring at us is this. That's your A, is A, and that's your B, which is 3b. And we are subtracting it, okay? So when you look at these three choices up here for your formulas, which one of those looks like A minus B? And I think I made a little mistake there. I meant to say that's regular B and not 3B. Sorry about that. So the one that matches that A minus B thing and with a funny looking trinomial right there is literally the second equation. Bam. Okay, there it is. That match. Let's check it. Is this A squared? Is this part right there AB? And is this part right here B squared? That's the question. And then it looks like it is, right? A squared is A squared. A times 3B is 3AB, the middle term right there. And 3B squared is 9B squared. So it does match that. So my answer is A cubed minus B cubed, which I need to bring down to here. So a cubed minus b cubed is what I'm going to put in from the original. A is a, b is 3b. So when I clean that up, I'll get a cubed minus 3b cubed is 333 is 27. And b cubed is b cubed. And there's your answer. Woo! Crazy. All right. Wow. This might be a good time to probably take a break or something, right? Go get a snack or something or use the restroom. I'm going to take a break myself. All right. I took a little break myself. I hope you did too. Let's move on to the next page. Here we go. Example 4. Beginning of this lesson, we saw Pascal's triangle. I'm going to go ahead and write it here on this page. Row 0, row 1, row 2, row 3, and so on. This is something that can be replicated very fast with very little memorization except for the fact that we're just adding the previous 2 numbers above it. I'm going to go far enough to help us out with the next few examples. Those are the row numbers. Okay. All right. The reason why I'm writing Pascal's triangle, because it'll help me expand x plus y to the 6th power, okay? Think of this as being a cool pattern. Try to imagine doing x plus y times itself 6 times. That's a lot of work. What Pascal noticed many hundreds of years ago is that it's linked to a pattern that's symmetric, okay? So think of x as a, think of y, the second half of this binomial, as b. We're going to expand this binomial using Pascal's triangle. Off to the left here. The power is 6. That's your n value. N is 6. Look at row 6, everybody, when n equals 6. We have 7 numbers there, 1, 6, 15, 20, 15, 6, 1. That is what we're going to use for the answer. This is a cool way to expand the binomial brought to a n power. It's very cool. Write down 7 blanks. 1, 2, 3, 4, 5, 6, 7. Okay? Put in those leading coefficients that you see in Pascal's triangle. 1, 6, 15, 20, 15, 6, and 1. Now, take your A's and B's and put them into the blanks using this pattern. A's go down from the highest power. So A in this case is x to the 6, and it goes down in each blank by 1 power. This is really cool that he noticed this many, many hundreds of years ago. Bam. B's go up from 0. The B in this case is y to the 0, and it ascends, so to speak. And this is the pattern. Isn't that crazy? We have 7 terms. You can prove this to yourself if you want to. Take x plus y times x plus y and do it 5 more times, and you'll see this will come out of it. Isn't that crazy? Now, let's talk about the power of zeros. Y to the 0 is technically 1. You don't have to write that there. And x to the 0 is 1 as well. You don't have to write that there as well. But your final answer is, dun, 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 x to the 6y plus 6x to the 5th y to the 1st plus 15x squared y squared plus 20x cubed y cubed plus 15x squared y to the 4th plus 6xy to the 5th plus y to the 6th. This is called binomial expansion. It's a shortcut using Pascal's triangle. Powers of A, let's remind ourselves, decrease. Power decreases for the A value. And for B's, that decreases from N. Forgot about that. B's powers increase from 0. And that's how that works, okay? Very cool. There's actually something called the Binomial Theorem that you'll see again in trigonometry. That'll help us with example 5. Any questions about binomial expansion example 4? Pretty crazy, it works for everything. All right, here's something called the Binomial Theorem. It's basically pointing out the pattern. The pattern is any binomial, a plus b to the n power, can be written with coefficients c0 through cn, and I'm just listing it generically. This is not a big deal. You don't have to memorize this, right? See that c sub 0, that's referring to this guy up here, x to the 6y. So c to the sub 0, a to the n is referring to that particular pattern right there, okay? Oh shoot, I just realized something. Typo. Example 4, that y is not there anymore, isn't it? Be careful. Y to the 0 is 1. Good thing I caught myself, yeah. Moving on to the pattern. The next coefficient, C1. The next coefficient, C2. Now take a look what's happening to the powers. I'm just generically writing down what happens sequentially. And this is called the binomial expansion. Okay, don't have to memorize that. All right. Let's do it again. Take a look at example 5. Use the binomial theorem to expand each expression. We're going to do the same exact thing. We're going to use Pascal's triangle. We're just theoretically calling the binomial theorem, okay? So a minus x minus 1 to the 7th power will be the n equals 7th row right there, okay? We're going to take those numbers and write them down here with 8 blanks, okay? 1, 2, 3, 4, 5, 6, 7, 8. We're going to take those coefficients and plop them down. Here we go. They are 1, 7, 21, 35, 35, 21. Isn't this crazy? 7 and 1. Great. We're identifying A and B. A is, take a look at A. A is X. Okay. B, be very careful here. B is not 1, it's negative 1. There's a minus sign right there. So A is X, B is negative 1, okay? All right, let's put that down. I'm going to use a different color so we distinguish it from the coefficients there. Kind of change the color a little bit on you. Sorry about that. B is -1. Okay, let's plot it in. The A values descend from n power. N in this case is 7. Okay. Look for the pattern. Here we go. So A is x. Let's put down x to the 7th power. Bam. X to the 6, and so on. I'm going to write those in. It's just easier to do it this way. And I don't want to write x to the 0. That's not necessary. I can just make that disappear. Okay? You just leave it out, x to the 0. Okay? Well, you know what? Let's just leave it in there. We'll cross it out in a minute. B's ascend from 0. Let's put that value in. -1 to the 0, and so on and so forth. Yeah, you're already anticipating what's going to happen with the negative signs, and they're going to kind of flip-flop back and forth, aren't they? We are applying something called the Binomial Theorem. Now we just have to clean that all up. Just a reminder, anything to the 0 power is 1. So that goes away right there, and that right there goes to 1 as well. Okay, let's clean this up right now. Okay, x to the 7th. Now look here in the second term, 7 times x to the 6 times -1. -1 to the first is negative, so it's -7x to the 6. Then over here we're 21x to the 5th, -1 squared. -1 squared is a positive, so that becomes a plus 21x to the 5th. And you notice it flips back and forth. X to the, so look at that, -1 to the 5th. That's an odd number of negatives. That means the whole thing will be negative, yeah? Okay. Ooh, what's this, -1? Yep, there it is. Ladies and gentlemen, there's your binomial theorem applied to the binomial expansion. Woo! Okay. 5b is the same, pretty much. Oh, look, 5b is just like example 4. We will have, we'll be looking at n equals 6, the 6th row here, okay? Well, technically the 7th, but anyway, we're going to have 7 blanks here. You notice that pattern there? The number of blanks is 1 more than the power. Let's identify A. A is 2C, and B is D. And we're just going to expand, okay, with 7 blanks because n equals 6. Yeah, and everything will be positive here. So we're going to have 7 blanks. 1, 2, 3, 4, 5, 6, 7. Okay, here we go. The row is 1, 6, 15, 20, 15, 6, 1. I'm going to put those numbers down in my blanks there. Looking up there in my Pascal's triangle. Here we go. All right. 1, 6, 15, 20, and then back again. Then I'm going to put in my A values. Ooh, 2C to the 6th power. This is a little bit of work here. We're going to have to clean those up. And then going up for B values. This is crazy. Whoops, that should be a 4th. Sometimes if you get distracted, you lose track of things. All right, I'm going to clean that up. Anything to 0 is 1. So that goes to 1, and that goes to 1 down at the back end. 2 to the 6 and C to the 6 becomes 64, C to the 6, okay? Plus, ooh, No more work here. 2 to the 5th power is 32 times 6 is 192. So think about what just happened there. That's 6 times 2 to the 5th. That was 6 times 32. That gives me my 192 c to the 5th d plus, you'll get 15 times 2 to the 4th. 2 to the 4th is 81. 81, did I say 81? I meant 16, sorry about that. 2 to the 4th is 16. 16 times 15 is 240. The next one is 2 to the 3rd is 8. 8 times 20 is 160. The next one is 2 to the squared is 4. 4 times 15 is 60. And 2 times 6 is 12. C to the 1st, D to the 5th, and plus D to the 6th. Wow. I mean, the alternative is to manually multiply 2c plus d to the 6th power. That's a lot more work. Might be a good time to take a break, folks. It's already up to an hour. What? That's crazy. All right. Habits of mind. For what binomial expansion is this particular thing? Now, this is interesting. Take a look at the first term. 243x to the 5th. So you know your expansion will be something to the 5th power. And you notice that there are minuses and pluses. So you know your second term will be minus. And at the end, y to the 10th will be can be brought to the 5th if you do y to the 2nd power. You see that? Y squared to the 5th, you multiply as y to the 10th power. And over here on this end right here, we know it's going to be some form, oh look, something to the 5th power will give me x to the 5th, that'll be just a single x to the 1st, right? So then you say, hey, is there a number brought to the 5th power will give me 243? The answer is yes. That number is 3. 3 to the 5th power is 243. I know that's not easy to recognize, but that's something that you might notice later on. That's your answer for that particular problem. Last page. All right. Ooh, down to the nitty gritty here. Let me zoom in a little bit so you can see a little bit better. We're asked to multiply with number 7 and 8. All we're doing is looking for patterns. Looks like we have something times its conjugate, a plus b times a minus b. So this is a product of a sum and difference. There's your sum. And there's your difference right there, okay? So this will give me, according to one of my formulas from way back on the front page, a plus b times a minus b will give me a squared minus b squared. So I need to get that over here ready for a squared minus b squared. A is 2x. B is 8y. Whoops. And then you clean that up and you're done. Because if you normally FOIL this, the O and the I disappear. Think about that. This is basically a product of a sum and difference, meaning these are conjugates, right? When you FOIL, the O and the I disappear. You don't have to worry about those other two particular terms. It's just F and L. And literally, we're doing F, the first terms, 2x times itself, times L, 8y times itself. Basically, that's all you're doing. So 2x squared is 4x squared, and 8y squared is 64y squared. And there's your answer. Yay. All right. The next one is a product of a sum, meaning with itself. Product of sums, meaning a plus b times itself. that will give you a pattern of a squared plus 2ab plus b squared. It's not the end of the world, remember, if you don't remember these patterns, but it's helpful when your problems are ugly. A squared plus 2ab plus b squared right there. A is x, b is 3y cubed. Put those numbers in, or terms, x, and 3y cubed, I meant, and clean it up. X squared plus, ooh, watch out here, 2 times x times 3 is 6x y cubed plus 3 squared, and y cubed is 9y to the 6. Okay, take care of that. All right, that takes care of multiplication. The next few problems is factoring or division. Number 9 is kind of crazy. When you look at all those choices, you realize what's going on here. We have a 36 and a 4 for coefficients. Sometimes you can squeeze a little bit out of that. In this case, you can take out a monomial GCF of 4. 4 can be factored out. That leaves you with a 9a to the 6 minus b squared. And from there, what's even crazier is that this binomial is not a perfect cube, it's actually a perfect square, difference of perfect squares. A squared minus b squared factors to be a minus b times a plus b. We just did that a second ago in the previous right there, right? We're just going backwards. We're factoring now, okay? We're factoring. Factoring is division. That's the key here. We are factoring. So knowing that information, the square root of 9a to the 6 is 3a to the third, half of that power. And the square root of b squared is b to the first, okay? That's your a right here. That's your a value. And that's your b value. That goes into these spots right here, 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 and here, okay? So that is a minus b times a plus b. And you put those values in. And you're done. That's the factor form of that problem, okay? Oh, whoa. We lost something, didn't we? That 4 we took out originally, yeah? Good thing I'm catching all these errors today. Oh boy. Losing my touch here. That 4, yes, was part of the original problem. Yes, there's my answer. Ooh. Number 10. What the heck is that? Y to the third? Nothing I can factor out for a monomial GCF from both of those terms here. Are those difference of cubes? Is 8x to the 6th cube rootable? Is y to the third cube rootable? The answer is yes. This is a difference of cubes. Crazy. The formula is a minus b times a squared plus ab plus b squared. I'm reading that from the previous pages from our formula. This is a difference of cubes now. A cubed minus b cubed. We'll give you the rest of those up there. Okay? A minus b. All right. We got to figure out what the heck a is. A, when you take the cube root of 8x to the 6th, is 2x squared. Okay? Because 2 times 2 times 2 is 8. X squared times x squared times x squared is x to the 6th. B is just simply y. Okay? B is y. Put those in there and you're done. Ooh, watch out, I got to square that in a second. And then I got putting the y right here, and a y right there, and a y right there. Clean that up. 2x squared minus y. This is where it gets a little tricky. Be careful. 2x squared squared is 4x to the fourth plus 2x squared y plus y squared. And there's your answer. Woo! Crazy stuff. Wow. Probably one of the longer lectures. M to the 8th for number 11. M to the 9th, sorry. Misspoke there. For number 9. Number 11. Getting long in the day, isn't it? M to the 9th plus 27 m to the 6th. Those are not perfect squares. 27 is not a perfect square. I can't take out a factor from either of those terms in that binomial. However, I'm going to guess it's the difference, I'm sorry, sum of cubes. And in fact it is. M to the 9th is cube rootable. When you cube root m to the 9th, it is m, take 9 divided by 3, it's 3. That's your a value, okay? And if you cube root 27 n to the 6th, you'll get 3n squared. There, ladies and gentlemen, are your a and your b values to be plugged into the formula from earlier. A plus b times a squared, I'm sorry, yeah, a plus b and a, okay, plus minus ab and plus b squared. All right, let's put those numbers in. M cubed. So I realize that I didn't write this down for the actual notes on my website. You might want to jot them down from here. B is 3n squared. And let's clean that up. M cubed plus 3n squared times m cubed squared is m to the 6th power minus 3m cubed n squared plus 9 n to the 4th. Holy cow, there it is. Ooh. All right. Number 12 and number 13 is like doing binomial expansion, but only focusing on one term answer. Now, a couple of things using Pascal's triangle here in a minute. I notice that n is 5 right there, which means I'll have 6 terms. 1, 2, 3, 4, 5, 6. Now in trigonometry next year, you'll learn how to do this with combinatorics. But right now, in this particular case, it's easier just to pretend we're doing the whole thing with Pascal's triangle. With Pascal's triangle with 6 spots using the n equals 5 row, it is 1, 5, 10, 10, 5, 1. We're looking for the 5th term. 1, 2, 3, 4, 5. We want this box right there. So I needed to do that to get my bearings on which term I want as an answer. So I wrote down 1, 5, 10, 10, 5, 1. And I know my powers are x to the 5, x to the 4th, x to the 3rd, x squared, x to the 1st, and that's the x. The y's go up, don't they? y0, y1, y2, y3, y4, and that's the easiest way to do this problem manually. 5x y to the 4th is the 5th term. Okay, I'm going to do the same thing with the next problem. In this case, I have n is equal to the 6th power. I'm going to throw down 7 blanks. 1, 2, 3, 4, 5, 6, 7. And I only need the 3rd term this time now. And after a while, you notice when you do put down the coefficients, 1, 6, 15, I don't really need to move further. And if you look at the first term here, I have a's, a to the 6th, a to the 5th, a to the 4th. And you notice something else interesting. The powers add up to n. Look at that, right? So if I put down the second half, -3, the power is Going to be 2 because 4 plus 2 will give me 6. So after a while, you see these patterns, and boom, clean that up and you're done. Now, these are not all variables for the terms. Negative 3 squared is negative 3 times negative 3 is positive 9. And this gives me as my final answer of 135 a to the 4th. And that's your answer right there, the third term. Okay? Woo! Okay. I'm actually going to let you try the next 4 problems on your own. I'm only going to put down the answers, and you can pause the video and move off with your life, but I'm going to put the answers here for the next 4 problems. Here are your answers. Good luck with them. Try them on your own. We're basically done. Spent a lot of time today. Hope you're still doing well. There's your answer for number 14. Here's the answer for number 15. Today was all about finding patterns. There's answer number 15, and then we got 2 more to expand as well, and here they are. And I believe these are not written down in the file. Okay. And here's the last one. This is a big one. And with that, ladies and gentlemen, we are done. Oh my goodness. Well, thank you very much. Have a good day. See you later.